Thank you very much. I think this is my third task test conference, and I think this one is a very special one because we are forced to be at home. But anyway, I think task test is always very special because I think I never saw so much interest from a student that the one I found there. So I think for me this has been always a very special experience, and I would like to thank the organizers, and in particular Nico, for the kind invitation. So the work I will present here is intended to show you how modest nuclear physics experiment can have an impact in a better understanding of neutrino physics. And actually, I am forced to cover many things to give a full flavor of the problem. And well, my talk looks roughly something like going through many things, small steps, trying to explain many things. So because of that, I will need to cover basic aspect of beta decay, and then talk about a little bit about neutrinos, and then talk about the technique itself. And I will apologize for repeating many trivial things that you might know. So the first thing I need to mention is, of course, that we use reactors to produce energy, and in reactors we use fission, and every fission is approximately followed by 6 beta decays, which means that the sizable amount of energy is released through the beta decay of the fission products. That amounts to approximately 7–8% in a working reactor, but this becomes dominant when you stop a reactor. This is from the perspective of the decay heat. But of course, from the perspective of the talk I'm presenting here, the important thing is that the reactors are the largest man-made Pacific sources of neutrinos, or in particular antineutrinos, since every fission is followed by 6 beta decays. After every fission, you have a mean value of 6 neutrinos, antineutrinos. And this immediately shows you the relevance of reactors in the discovery of the antineutrinos, or the neutrinos. So the neutrino was postulated by Pauli in 1930, but actually it took several decades to discover it by the experimental Reines and Cowan, in which they used the reactor flux at the Savannah River reactor using the inverse reaction. So neutrinos, well, in general, neutrino physics have grown to become a fascinating field. I think mainly, well, apart that they are very difficult to detect, they can provide information about very harsh environments. So you can imagine the neutrinos coming from a supernova, for the sun, from the center of Earth. And I think it was mentioned by Eric that there was a recent paper in Nature commenting that for the first time, I think a week ago, it was published. They showed that the neutrinos coming from the CNO cycle were detected for the first time. So what makes the neutrinos difficult, apart from the difficult to detect them, is that they are produced and detected in flavors. You have the 3 flavors here. And the propagation of the particles in space depends on mass, and the eigenvalues of the weak interaction and the mass eigenstates, they do not coincide. So they are connected by a matrix. And actually, if you do the algebra, you see that when you are propagating the free particle in space, they can change flavor. And this is what is called the oscillation phenomenon, which also immediately shows it was one of the first evidences of physics beyond the standard model. So it is important for neutrino physics to determine this mixing angle that in this particular simple case governs the probability of one neutrino that is produced as an electron neutrino oscillates into another flavor, which means that you might not be able to detect it. So for those experiments, reactors, of course, are important. And one example of experiment is the WHO experiment, in which you can put a neutrino detector close to the reactor and another one far away. And by comparing the flux of the neutrinos that you detect, you can say something about the mixing angle. Well, for those experiments, it is important to determine the primary antineutrino spectrum. And actually, there are a very few alternatives for doing that. I mentioned here 3, but in reality, 2 are very interconnected. So one is a so-called pure conversion procedure that is based on measurements that were performed at the ISOL reactor in the 80s, 90s, and actually what they did was to bombard a thin target of fissile materials and to detect the conglomerated spectrum, that beta spectrum that is produced after fission. And later, using complex conversion procedures and assumptions, they converted that beta spectrum into antineutrinos. This was a very important step for neutrino physics, and actually later there was a revision of this conversion procedure. We have become known as a Hubbard-Muller model, which have become actually the standard of the reactor physics for calculating the antineutrino spectra. There is another alternative I will talk later, which is closer related to the work we are doing. So what are, you might think, well, 2012 was actually a fantastic year for neutrino physics because the major reactor neutrino collaborations or experiments published the theta 1.3 value, which was larger than expected. Actually, this was a surprise, opening for new possibilities in neutrino physics. But actually, it happened that there was also a problem. So this became known as a reactor anomaly, which is known as the deficit in the number of antineutrinos that you detect at short baseline, so those detectors that are close to the reactor, compared to the prediction of the Hubbard-Muller model, which I mentioned before, have become the standard. So this attracted considerable attention because it can be explained by the existence of a possible sterile neutrino. Well, can be considered a kind of normalization problem. But if you normalize, if you forget about that, and then if you normalize the measured spectrum to the prediction of this model, you will obtain pictures like this. And this was published, for example, by the Reno collaboration. And you see that there is a discrepancy also in the spectrum. So this has become known colloquially as the bump in the spectrum, which is a spectrum distortion around 5 MeV when you compare measurement with this Hubbard-Muller model. So this calls for an alternative model for calculating the antineutrino spectrum from a reactor, and this is somehow what we have been involved. It doesn't mean that we are the fathers of this model. So, and actually the alternative is to do what is called summation calculations. And actually it's based on the following. If you know a beta decay properly, and by knowing properly a beta decay, I mean that you know the spin and parity of the state, parent state, the state that you are populating in the daughter, and the intensities by which you populate those states. So if you know that information, actually first, you know the information of the spin and parities, you might calculate the shape of the beta spectrum, and also you can calculate the shape of the antineutrino spectra for a particular transition, beta transition. And if you multiply by this normalized intensity and sum over all the branches that happen in a beta decay, you might have the beta spectrum or the antineutrino spectrum for a particular beta decay. But of course, in a reactor, you are producing of the order of 1,000 fission products. So you need to calculate for all of them this antineutrino spectra. And if you sum over them, and this is what is presented here, this is what is called the summation calculation. So in particular, what you are doing is multiplying the activities of the fission product times the spectrum that you can calculate. So this is very similar to what can be done for calculating the decay heat in reactors. That is what I mentioned before, that this is energy released by the fission products, which is relevant for the security of the reactors. Now I will emphasize how we determine this number, which is look like this is not a so difficult problem, but in reality it's not so easy. Because if you measure the beta spectrum with the silicon detector, for example, you will get a spectrum that looks like this. That if you have more than one transition, it's very difficult to disentangle. So to solve this problem, normally what we do is to use germanium detectors that have a fantastic energy resolution, and then you construct the level scheme of the beta decay, and from the intensity balance of the gamma populating the level and the exciting them, you extract the probability of going the so-called psi feeding, that in this case is in particular the beta decay. So this means that you need a good germanium array for measuring this, and then you need to construct complex level scheme to be able to determine this feeding. Well, it happens that in many occasions you don't have enough gamma intensity and you miss several gamma rays or many gamma rays. It means that you, at the end, you construct a level scheme which is not correct, and you assign beta feeding to a lower line levels. And this is a systematic problem because you don't know it's happening. And this has become in the literature as the Pandemonium effect. Actually, Pandemonium stands from the capital of hell, and this was introduced by Hardy and co-workers in this publication. So what you should remember from this is one of the lessons, the things that you should remember, that if you build level scheme with germanium arrays, it might happen that you miss some gamma rays, and because of that, you will end assigning feeding to the lower line levels, and this means that your beta intensity is displaced somehow to the lower line levels. So this is what is called the Pandemonium effect normally in the literature. So the solution is to increase dramatically your gamma efficiency, which means use a total absorption spectrometer that you can construct using a big detector around your source. And by doing that, actually, you are not interested anymore in detecting the individual gamma rays that follow the beta decay, but you are interested in detecting the gamma cascades that follow the beta decay. So an ideal detector will measure such a simplified beta decay that it will look like that. So you will have a peak, which is very similar to the peak of the feeding in this simplified case. But of course, life is always more complicated. And since you cannot build a 100% efficient device, you need to rely in solving this equation, which is a nasty one, to extract the feeding probability. This equation means that the spectrum that you measure is equal to the response function of your spectrometer times the feeding distribution that you would like to extract. This is not an easy task, and probably will not have the time to explain that in detail. What I wanted to show first is how real spectra looks like, for example, from a measurement of a cobalt source that we use conventionally in our laboratories. You see here the kind of a spectra that you will see with a germanium detector or with a small sodium iodide detector. And you see that you only see two very well-defined peaks that corresponds to this gamma cascade. You see here a TAS spectrometer that we constructed for the DESPEC collaboration. It is not a 100% efficient device. And you see, for example, here a TAS spectrum taken from the thesis of our student Victor Guadilla, where you see that the spectrum is dominated by the sun peak. You see also, this is the feature I mentioned before, but you see also escape peaks that are associated with the fact that this detector has not a 100% efficiency. So another thing I would like to mention before I enter more into details is if you do this kind of summation calculation, so you will use decay data, you need the individual beta decays, and actually the problem is that if you have data, and it can easily happen, that suffer from the Pandemonium effect or the Pandemonium situation, you will have an overestimation of the beta energies, an overestimation of the neutrino energies, and underestimation for the mean gamma energies that, for example, you release in the beta decay from the perspective of the decay heat problem. So I think I mentioned already that I will not have time to explain the complexity of the TAS analysis. If someone is interested, I can mention that later. It's a so-called ill-posed problem. My colleague Jose Luis Tain has done a fantastic job in improving how we can solve this problem. But what you should remember is that data, the spectrum that you measure, is equal to the response function of your spectrometer that depends on the decay that you are studying, multiplied by the feeding distribution that you would like to determine. We need to solve that equation to extract the feeding, the beta feeding pattern. So this is how a typical total absorption spectrometer will look like, an experiment, let's say. So you will have a radioactive beam that is implanted in a tape, and then it's surrounded by a a large scintillation detector, normally constructed with sodium iodide, and you can couple that measurement with ancillary detectors you would like to see coincidences and so on. You measure for that while, and then you move the activity using a tape system in order to avoid the contamination of the daughter activity of the sources that you are interested in measuring. The measurements I will talk about here have been done in Uvascular, what we call our favorite place for polar experiences. And you see here a list of many nuclides that we measured there, many decays. And we went there because actually many of these elements are refractory elements, and they have developed there something which is called the ion guide technique, which is based on the following. So you bombard a target with a proton beam, and then the reaction products came out of the target, and they are transported through a differential pumping system to the accelerator stage of the mass separator, which means that you have an ion source which is chemically independent, which is very important for extracting these elements that I mentioned you before that are refractory. So apart from that, there is, well, we have very good friends in Uvascular, but apart from that, there is another thing also. So you have a separator which has a modest mass separating power, but then there is a penning trap. Actually was already mentioned here in this school, the relevance of penning traps for measuring masses. So, and using the penning trap, you can have, if you further separate the radioactive beam, you can have very clean, isotopically clean sources after the trap for the measurements, which is very relevant for this kind of studies where you are using a calorimeter. So in 2005, 2006, we started with my colleague Jose Luis Taín a project for measuring beta decays that are relevant for the prediction of the decay heat in reactors. And actually, we measured several cases that were included in the thesis of Dolores Jordan, and you see that these 7 cases has a very large impact in the improvement of the reproduction of the decay heat in 239 plutonium. This was immediately recognized by the NAND group, led by Muriel Falot, who implemented that data in the summation calculations that they do for antineutrino calculations. And you see here the impact of including that task data with or without in the antineutrino summation calculation. This is a relative ratio. And you can see here that the impact of these 7 nuclides was of the order of 8% for plutonium-239. Actually, from this measurement, we realized that the 7 decays were suspected to be pandemonium, but only 5 were really suffering from the pandemonium effect, which shows you the relevance of doing these measurements. So you might wonder if this problem is at all feasible, because in fission, we are producing of the order of 1,000 fission products. And to show you that this is feasible, I took a transparency from Alejandro Sonsogni, who did a summation calculation based in this database and compared it with the ILL conglomerate beta spectrum. And you see that the agreement is not nice, but this is not the point of this figure. The point of this figure is to show, you see, this is a kind of, I call a spaghetti plot, because every line represents a fission product, the decay of one fission product. But you see there are a few that are outstanding. They are more important than others, which reminds you of the great writings of George Orwell. But actually the message here, which can be taken from this article, is that the 75% of the spectrum can be accounted by 50 or fewer transitions. So if you identify those beta transitions, you might be able to tackle a large percentage of the antineutrino spectrum. And this is what we have been trying to do. The first step was the identification of the most relevant players by the NAND group. Actually, they have been playing a key role in these measurements. And you see here that among those cases, this is a table which shows the relevance of the different cases. This table is published in this article. 92 rubidium is a start case because it contributes alone to 60% of the spectrum in this range. And in one of the last energy beams, it amounts to approximately 38%. So In 2009, we did an experiment in Uvascula aiming for the measurement of some other cases, not of relevance for this problem, but we already included some rubidium isotopes which are relevant for this problem. And you see in the next slide, in this slide, the analysis of the task measurement of the 92 rubidium, which is represented here by the black line, and is compared with the spectrum but that you can reconstruct after the analysis, which means multiplying the response function times the feeding distribution that we obtain after the analysis. And this, in particular, was analyzed by Zachary Isofu from Nantes. And the most relevant thing from this case, which is not a really Pandemonium case, is that from this experiment we were able to measure properly the ground state feeding of this beta decay that have been changing in the nuclear data evaluations from 94% to 50%, etc. So this was a relevant measurement. And you see that immediately here. This is a figure taken from an article by Muriel Fadot, from this, where you compare the impact of having a 51%, for example, for the ground state feeding of 92 rubidium with the value that was obtained in this measurement. And this can have an impact of up to 20%. Again, this is a typical figure I was showing with or without including the new task data. In 2014, we put we did a new experiment, but this was only focused on cases that are important for the antineutrino prediction of the spectrum. Sorry. And here in this list, we wanted to address very challenging cases, some cases that are produced in isomers in fission. For example, the niobium isomers that you can have, these are very difficult to disentangle because they have isomers that have very small excitation energy, and they have beta decay half-life that are very similar, which means that if you want to disentangle the beta decay of this isomer with respect to the other, this is a very challenging task. And they are relevant because they contribute of the order of 5% to a cumulative fission yield. And actually, these cases were analyzed in the framework of the thesis of our ex-student Victor Guadilla, who did a fantastic job, and we were able, applying all the tricks of the penning trap and also to disentangle, playing with the half-life, etc., to disentangle the contribution of the different isomers. And you see here the analysis of the ground state isomer of 102 niobium, and you see here the feeding distribution that was obtained from this measurement that was published in Physical Review Letters, compared to what was previously known in high resolution. And you see here the separated high excitation isomer, which is a low spin isomer, and this was even more relevant because nothing was known previously from this case. And you see the impact of the 4 niobium isomers, again, in this kind of plot, that amount to up to 12% for the plutonium, and of the order of 6% for the uranium-235. So after all this work, we were working like ants, studying individual beta decays to be able to contribute to the antineutrino spectra. The Nantes group performed a new summation calculation, putting together all these task measurements. And this is what you see here. The black line, so this is a ratio of the diabase experimental data with respect to a summation model or the Huber-Muller model. And the black line here is the summation model now, which includes all the task data, and the discrepancy with the line of 1, which is the perfect agreement, is of the order of 2%. You see that there is a larger disagreement here, but the most relevant part from the neutrino flux is here in this energy range. And you see that this summation calculation is now doing better than the Huber-Muller conversion model, which was considered the standard of the field. And you see here actually the discrepancy of the order of 6% that was considered the reactor anomaly. So the question that immediately arises is if this is still a living anomaly or not. And you can go beyond that. Actually, the Nantes group was able to calculate the what is called the inverse beta decay yield, which is represented here, versus the percentage of plutonium-239. And you see here that this is a line, the experimental data from Diabate, they are able to do that. And if you increase successively Pandemonium data, you get a nicer and nicer agreement with the Diabate data. So we are now above the order of 2%. This is relevant because actually it's opening a window to new physics and application. It can be also relevant for future antineutrino experiments like Juno and Tau that will address fundamental questions like the mass hierarchy. But apart from that, actually, the major goal could be that at the end, you might see the final structure of the antineutrino spectra, which will reflect what is going on inside the reactor. And this can be also relevant for non-proliferation applications. We are not yet there, that you can put an antineutrino detector outside the reactor and disentangle if there are illegal manipulations with the field. So I think I am almost finished with my message. I hope I have shown you that the task technique can contribute to the improvement of nuclear data, in particular for neutrino applications. I was not able to explain in full detail how all these measurements are done. I can tell you that they are careful, but there is still a lot of work to be done because even though we are close around the 2%, there are still many beta decays that should be studied, and there are still several things that play an important role in the prediction of the antineutrino spectrum that should be addressed. And I would like to thank, in particular, all my collaborators and the PhD students and postdocs that have been hardly working in this field, and my collaborators, in particular Jose Luis Tain, which I would have been working in this field, and the collaboration from NAND and Uvascula, who have played a key role for obtaining these results. And since the reactor anomaly is almost dead, I was wondering if we can create the task test anomaly, because I think even Bohr was challenged by the question, and inspired by the quantum mechanical teaching of John Wood, I think this is a good expression for the task test wave function. Thank you.
Thank you very much, Alejandro, and for all your contribution for the past many years you've been coming to the test. We learned so much from you. So there are questions on the chat from Vivek. Vivek, do you want to unmute your mic and ask straight to Alejandro?
Yes. Yes, can you hear me?
Yes.
Yes.
Can you hear me?
Yes.
Yes.
Okay. The question is, the first question I think you already answered in your slides, namely, what is the magnitude of this anomaly? So it looks like now it is about, after the new measurements, is about 2% level, right? The 5 MeV anomaly.
Well, actually, the anomaly was called because there was the flux that you can obtain from the model was not reproducing the data from the short baseline experiments. But of course, you should look at the error bars of these calculations. So there have been many factors, many things that have been identified that are important also. For example, the role of first forbidden transitions and some of the corrections that are taken into account for the calculation of the beta or the antineutrino spectra that play a role. So I think probably this problem of the anomaly was somehow overestimated, but it has attracted a lot of attention, of course, and there are many experiments related to that, actually trying to measure the antineutrino spectrum of uranium-235 close to the reactor in several places, and I think there will be very interesting results coming. Well, they have already many publications related to the topic, but there will be still many results coming from this topic in the future.
The other question, thanks. The other question relates to, how many important nuclei need to be measured for the lower part of the energy spectrum?
Oh, for the lower part, probably many. But as I said, probably these beta decays are better known. So I think you should choose for this so the cases that were mainly identified, the arguments we were used for identifying these cases that was done, work mainly done by the NAND group. Actually, you look for large beta decays, cases that are dominated by large fission yields, and also you see that many cases that have a very large ground state filling.
Yeah. Okay. Thank you.
Thank you very much. So there's another question on the chat. You can answer it. So next we can have Professor John Shapishefa. So you can type the answer on the chat, Alejandro.
Okay.
Yes, thank you.